Let's look at OpenStax College Physics, Chapter 18, Problem 61. Figure 1857 shows an electron passing between two charged metal plates that create an 100 Newton per Coulomb vertical electric field perpendicular to the electron's original horizontal velocity. These can be used to change the electron's direction, such as in the oscilloscope. The initial speed of the electron is 3 times 10 to the 6 meters per second, and the horizontal distance it travels in the uniform field is 4 centimeters. A. What is its vertical deflection? B. What is the vertical component of its final velocity? C. At what angle does it exit? Neglect any edge effects. So let us start out by writing out the knowns and the unknowns. So we know that we're dealing with an electron. So from a table, we know that the charge of the electron is negative 1.6 times 10 to the negative 19 coulombs, and the mass of the electron is 9.11 times 10 to the negative 31st kilograms. Then we know that there is an electric field of 100 newtons per coulomb, and it's directed straight down. And the initial velocity of the electron is 3 times 10 to the 6th meters per second. And it travels a horizontal distance x of 4 centimeters. And then in part A, we're looking for the vertical deflection. So we want to know what y is. In part B, we're looking for the vertical component of its final velocity, so we want v final y. And in part C, we want to know the angle at which the electron exits that electric field. So let's follow again what's going on here. We have an electron traveling in the positive x direction. We're given the x and y directions here. And it will follow this path. Now, the reason it follows this path is that whenever we have an electron in an electric field, so if I put the electron here, it is experiencing a force, and basically we know that the electron is attracted by the positive plate here. So this is the electrostatic force it experiences, and this electrostatic force is the charge of the electron times the electric field. So that is the force that's acting on it. As a result of that, since the force is perpendicular to the velocity, the force does not change the horizontal component of the velocity, but since it gives the electron an acceleration in the positive y direction, then the electron will pick up a y velocity and it will then be deflected. So let's see how long the electron was in the electric field. So we'll start out by saying that the velocity in the x directions of the v naught is distance, horizontal distance divided by time. So that means that the time that the electron was in the electric field is x over v naught. Then we know that in the same amount of time, while the electron traveled in the horizontal distance, it also picked up y displacement. So in the y direction, just like for projectile motion, we can say y equals y naught plus v0 yt plus 1/2 a yt squared. And we can measure the distance from the point where the electron comes in. So this is going to be my y initial, and that's a 0. Then we know that the electron didn't have an initial velocity in the y direction. So we're left with y is equal to 1/2 a sub yt squared. Now we know t from the horizontal velocity and displacement, but we don't know the acceleration. However, we do know that there is an electrostatic force that causes the y deflection, And then when we write Newton's second law as sum of the forces on the electron in the y direction is mass times acceleration in the y direction, then we can say that the electrostatic force, which is charge of the electron times the electric field, is equal to the mass of the electron times the acceleration in the y direction. So we do know now the acceleration in the y direction. It's the charge of the electron times the electric field divided by the mass of the electron. So if we put everything together now, we end up with the y displacement as 1/2 the acceleration in the y direction, which is charge of the electron times the electric field divided by the mass of the electron times t squared, which is x over v naught quantity squared. So let's insert the numbers here. Charge of the electron. So I have it written here as negative 1.6, but the direction of the force already takes into account the negative charge that's attracted to the positive charge. So I will take just the absolute value of the electron's charge here. So that is 1.6 times 10 to the negative 19th coulombs times the electric field, which is 100 newtons per coulomb, divided by the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. And x is 0.04 meters, divided by v naught, which was 3 times 10 to the 6th meters per second. And when we plug these numbers into our calculator, we end up with a deflection of only 1.56 millimeters. Now, in part B, we're looking for the final velocity in the y direction. So we can use another kinematic equation. So we'll say Vy equals V naught y plus AT. And we know that V naught y is 0, so this leaves us with the acceleration in the y direction, which was E divided by mass of the electron, times time, which was x over V naught. So that's 1.6 times 10 to the negative 19 coulombs times 100 newtons per coulomb divided by 9.11 times 10 to the negative 31st kilograms times x, which is 0.04, divided by v naught, which was 3 times 10 to the 6th. And this comes out to 2.34 times 10 to the 5th meters per second. So now we know the velocity in the y direction, and we know that the velocity in the x direction has not changed because there was no acceleration in the x direction. So that means that we can figure out the angle by just doing inverse tangent of Vy divided by Vx, which was just V naught, and that will be inverse tangent of 2.34 times 10 to the 5th divided by 3 times 10 to the 6th. And that is 4.46 degrees.